In this video, we're going to have a look at sulfonium ylides. What's a sulfonium ylide, you ask? Well, I'm going to show you. We start off with this compound here, which is just a thioether. It's a sulfur analog of an ether. Sulfur, of course, is a great nucleophile, and you can alkylate that sulfur. So the way you do that, of course, is just let the sulfur attack a alkyl halide, particularly one of a good leaving group like this one, and you'll get this sulfonium ion, which is a sulfur analog of an oxonium ion. Now, what's interesting about this, if you treat it with a really strong base, and what I'm going to use is hydride. So let me get a hydrogen here. I got to put a hydrogen on here, but then I want a hydrogen as a reactant, a hydride as a reactant. You can deprotonate this, and of course, when you deprotonate, what's going to happen is you're going to form a double bond to the sulfur. So here we're forming a double bond to the sulfur, and this is our ylide. This is the H2, looks kind of weird, but this is the species you want here. This is our sulfur ylide. It's a compound of sulfur with double bond to carbon. Of course, that sulfur still has a lone pair, and of course, this is because sulfur can expand its octet. Now, what can you do with these sulfur ylide? Well, the key thing is it can transfer this CH2 group, and let's see how this works. So let me grab a copy of the ylide. Okay, and what does it transfer to? Well, it transfers to carbonyls. So let me draw out a simple ketone here, and see how this works mechanistically. So here's our ketone. Now the reaction is that this is basically a nice nucleophilic group. So the double bond will reach around, attack the carbon of the carbonyl, pushing the electrons onto the oxygen, forming a tetrahedral intermediate. That doesn't look very good. Let me redraw it. Here's our tetrahedral intermediate. And this tetrahedral intermediate, of course, has this O- right here, and next to it on this carbon is the sulfur with a cation charge. That's a good leaving group. So what can happen is the O- just comes around, backside attack, a nice SN2 reaction, kicking out the sulfur. And what we've made, of course, is, if you follow the arrows, an epoxide. So here's our product, and we get our original thioether back, and our net result here is that we've made an epoxide from a carbonyl. Now this is very interesting because normally you think about making epoxides, you take an alkene and you use a peracid and you add an oxygen atom. Here we've started with a carbonyl and we've added a CH2, so we've completed the epoxide in a way completely different than the way we normally do it. Now there are some other sulfur ylades as well, and in particular there are ones which have extra stabilization. So let me just start over here, and I'm going to again start with the thioether, but this time what I'm going to do is I'm going to alkylate it with this ester grouping here. So we're going to have an ester. Okay, but I want to do an alkylation, so I'm going to use this bromide. So this will also work very nicely. The sulfur will just come around. Oh, that didn't work. Sorry. Let me get my arrow. The sulfur will just come around and displace the bromide. Here's the product, and again this can be deprotonated. And let me use the what am I doing? Let me let me use the hydride again. Here's the hydride. Hydride is nice just because it's good and clean, and we need to put it in there. So click there, and of course this is going to form an enolate because it's next to that carbonyl. and we get this stabilized. We get this what's called a stabilized ylide. It's stabilized because it's zwitterionic. So we don't have a sulfur carbon double bond, or at least we're not drawing that resonance form. We're drawing instead this resonance forms, which puts a negative charge out onto the oxygen. This is still basically an enolate, but this enolate is actually less reactive than some, and this lack of reactivity is somewhat important. So let's see how this works. Well, if we just allow this to react with our same ketone as we had before, we get carbon. We get the same reaction. So we draw out the ketone again, and so this is going to do the same reaction as it did before. Except now, of course, the enolate is going to react. So bring the electrons back from the oxygen, bring this around, attack the carbon out onto this oxygen. We'll have our new tetrahedral intermediate. Having some trouble here today. There we go. What's going on? And so now, again, what we want to do is have the oxygen kick out the sulfur. So O come around to sulfur. Out it goes. Wrong button. There we go. This is going to be off the page, unfortunately. Here's our product, which is again a cyclo, again is the epoxide. So again, we've added this to epoxide. Now, if that was all there is to it, you say, well, these stabilized ones are no different than the regular ones. But the fun is, let me get rid of this products, and I'm going to change the reactant. Didn't mean to do that. So what I want to do here is having trouble here today. Something's acting up. Again, too many carbon, not oxygen. Put in our carbonyl. What I've drawn now is a conjugated carbonyl, because these stabilized ylides will not go for the carbonyl directly. They're less reactive, and so it's kind of like when we compared methylithium to a cuprate. Methylithium directly would go to the carbonyl, and a ylide which is not particularly stabilized will also go directly for the carbonyl. But a stabilized one like this will go for conjugate addition instead of regular addition. So we're going to, again, let me just make that a little bit bigger. We're going to have the oxygen bring the electrons back, have our enolate come over and attack, but now it's going to attack conjugatively. And so again, we push the double bond over, electrons out onto the carbon, or out into the oxygen. Conjugate addition. Conjugate addition gives this product, but now the same thing happens as before. We're going to make a three-membered ring, but of course we're not going to make a epoxide, because when we come back, I hit the wrong button. Arrow. We come back to reform the carbonyl. The enolate is going to now come over and do a displacement of the sulfur. So it's going to attack that carbon, and the sulfur is going to be kicked out. And when we're done, we're going to have a cyclopropane. So this is kind of fun. Is if you have a standard sulfonium ylide without a stabilization group, it'll only add to carbonyls. If you have a stabilized ylide, it'll add to a carbonyl of a simple ketone or aldehyde, but a conjugated one, it'll conjugate addition instead and make a cyclopropane. So if you're adding to a carbonyl, you get an epoxide. If you're adding to the double bond of a conjugated ketone, you get a cyclopropane. So it's pretty neat chemistry, and you can have some fun with it.